Okay, now as we're picking up for the next two sections, or the last two sections, we're going to do the same thing that we did before. So we're going to flip the switch into the new position because there's nothing else we can do at this point. We have everything that we've calculated. So when we look at what we're doing, we bring up our circuit. So our circuit is going to continue with the same pattern. I'm going to have the meter sitting over here connected to the black probe. The meter is then going to connect to R1, which we know was 75 ohms. R1 is then connected to R2, which we now figured out was 3.6 kiloohms. And then we go from there into R3, which we're going to solve for. And then my switch is then going to be in position C. So position A was right there between 1 and 2. Position B is here between 2 and 3. And position C is right here after R3 going into R4. But again, there's nothing connected to the other side of R4, so we don't have to worry about it. So position C is then going to be connected to our switch. And from there, that connects to our positive probe, the red probe of our meter. Keeping all the same values, so R1 we kept at 75, R2 we kept at 3.6 K. My I meter is the same at 500 microamps, and my R meter was set at, or measured at 325 ohms. So as I go through with this position in slot position 3, or set position 3, now what I want to do is be able to measure a maximum of 20 volts on this same scale. So what I have here is the same process. I already know what my currents are going to be because I'm basing it off of max current, max voltage. So I know that from position A, we're going to have 200 milliamps between that one to our negative probe. We know from this position here at B, that's going to be 2 volts. And so now we have our 20 volts, and we have to look to see what is left. Using Kirchhoff's voltage law, we know that 2 volts is already here between R2, R1, and the meter. So out of the 20, the rest of it has to be dropped across R3. So the voltage of R3 then just simply becomes the values of 18 volts because we have our 20 minus the 2. And give me just a second. My tablet died to be able to write on. There we go. Now it's back. So VR3 is going to be that 20 volt max coming in minus all the voltage drops we already know, which is 2 volts, leaving VR3 has to be 18 volts because of Kirchhoff's voltage law. We know that we have 20 going in, we have to have 20 being dropped, so we have to have the rest across this. And then it's just a simple matter of my R3 value is then just simply the voltage of R3 over the current of R3, which we know is the same going through that meter. So I have 18 volts divided by my 500 microamps, and R3's value comes out to be 36 kiloohms. Okay, and then the next step is, again, we're to the same point where we have all the information we can. There's nothing else we can calculate, so we have to throw it into the fourth position. So what I end up here is I have R4, and my switch is down here in position D. Here is position C, which goes into my R3. My R3 goes into position B, which then goes into resistor 2, which then goes into position A, which then goes, into my meter after it goes through R1. Then it goes to the meter, then it goes to my negative probe, and over here, that is where the positive probe is. So then we bring everything with it that we've solved so far. So we've got 75 ohms here, 3.6K ohms here on R2. R3 was 36 kilo ohms. We have our I meter of 500 microamps, and we have our R meter of 325 ohms. All right, so exact same process as we did with the other one. We know coming in that in this setting, we want to be able to measure up to 200 volts. And by doing that, position 1 again has 200 millivolts sitting across there. From position B all the way down, that has a total of 2 volts there sitting there. Position C has a total of 20 volts sitting across everything. And position 4 means we have 200 volts sitting across from D to our negative probe, which means that following the same pattern, my VR4 is going to be the exact same as formula as what we had before. So VR4 is equal to the 200 volts minus the 20 that we've already counted for from everything from 3 down. So that means my VR4 is 180 volts. R4's value is then simply the voltage of R4 divided by the current of R4. And we'll just fix that. So I get 180 volts over 500 microamps, and that gives me a grand total of 360 kilo ohms for R4. That does not want to stay as a 4. All right. So now, based on our meter, based on the voltages we're looking at, we have now determined what all of our resistors need to be in order to build this thing, which makes it really cool and really easy. We can go into the lab, we can test this, and we can see those exact same values. All those voltages will pop up, and we'll be able to see exactly how this thing works. Now, one of the last things we have to take into account is a term that we're going to call selectivity. So I'll scroll down a little bit farther. And up here what we have is selectivity. So selectivity, this is the amount of ohms per volt that we have in our meter. Meaning, based on the amount of voltage we want to measure, we're going to have this much resistance in our meter to solve for it. And so what we do is the selectivity is going to be the same across each range. So across all ranges. If you get a different value, something you didn't calculate correctly. So what we do is as we go through and look at this, we got to look at our total resistance and the total voltage that we're trying to measure. So we have total resistance, so total ohms divided by total volts per range. Okay, so how we want to do this is let's put this up into range 1. So at range 1, what we had was R1's value plus the meter coming into our probes like this, and we were measuring 200 millivolts. So our total voltage for the range, we've already got. It's right here. We don't have to worry about that value. And so then we got to go back and figure out what all of our other values were. R1, if we remember, was 75 ohms, and the R meter was 325 ohms. So then what we got to do is we're like, okay, what is my R total for range 1? Well, all we have resistance-wise in this circuit is those two components. So my R total for range 1 is R1 plus the resistance of the meter. So my resistance of R1 was 75 ohms plus my 325 ohms of my meter gives me 400 total ohms. So then to find my selectivity of this, I put my 400 ohms over my 200 millivolts. I do that calculation, and what I get is 2 kiloohms per volt. Okay, so that's how we're going to calculate it. We'll talk a little bit here in a minute about what this is actually going to mean. So then we look at the other ranges. Our total for range 2 was R2 plus R1 plus the resistance of my meter. So we know that R1 in the meter was 400. We just solved that previously. Plus R2 was 3.6 kiloohms. So adding those together, so my R total for range 2 is 4,000 ohms. My selectivity was 4,000 ohms over 2 volts, which breaks it down to 2 kiloohms per volt, which should match my range 1 values. Okay, and then we're going to check the other ones. So here we've got my R total for range 3. So I have R3, R2, R1, and my meter. We know everything from that point because we did that calculation is 4K. R3 was 36K, gives me a grand total of 40K. And then I put the same calculation. I do my 40K over my voltage, which range 3 was 20 volts, and again, 2 kiloohms per volt. So far, out of 3 of our ranges, they have all matched up. The very last range, same process. The R total for range 4 was R4 plus R3 plus R2 plus R1. We know everything previous to that was 40K, and R4 was 360K. We add that together, we get 400 kiloohms divided by 200 volts, and again, 2 kiloohms per volt is what we call for our selectivity. Okay, so no matter which range we do, we take the total resistance in there and divide it by the total voltage that we're trying to measure, the maximum values that we could possibly have. Now, the reason for this, and this starts getting into the topics that we're going to talk about in week 3 when we start looking into parallel circuits. So if we look at how a voltmeasure is measuring the circuit, we have a basic circuit. We've got our DC supply. We have a couple of resistors. We'll just do it this way. So we've got R1, we've got R2, and we have R3. I'm going to put 10 volts across this thing. Let's put a 2K resistor here. Let's do a 3K resistor here. And down here, let's do a 5K resistor. So how this is going to go is with the total resistance we have in this circuit, it's going to be 10K. So what we're going to have is R1 is going to be able to drop 2 volts. R2 is going to drop 3 volts. R3 is going to drop 5 volts. And we can go through and check that using any of our methods, the voltage divider, finding the current, using the current to find voltage, whatever it is, but just knowing quick and dirty that that's what the values are that we should expect to see. So what happens is when I come in to measure voltage, voltage is one of the things that I do not have to disconnect my circuit. So if I wanted to measure the voltage of R2 again, I'm going to bring out my voltmeter and I'm going to plug it in across R2 while it's in series or while it's in the circuit. So my red lead is here, my black lead is over here, and what happens is when I put my voltmeter into the circuit to measure this, I now have a parallel connection between the voltmeter itself and R2, which means I'm going to end up getting a little bit of current that flows this direction, as well as the current that's supposed to be flowing through here through R2. So my voltmeter actually steals a little bit of current, which we will talk about more in week 3. So don't be worried about exactly how it works. We're going to cover those later, but just kind of take it right now that this is what it does, and we'll talk about some of the reasons behind it later. So now I get this little bit of current coming through here. Now what happens also, depending on the resistance of this meter, it's going to affect the resistance of this guy, of the component that it's in parallel with. And we want this, our voltmeter, to be as high as it can against this value. Because when you put things in parallel, you get values that end up smaller than what this value is, or whatever the smallest value is. So if we had 100 ohms of resistance across this guy, this 3K becomes 100, or just under 100. So we want this value here to be very, very large compared to the resistance of R2. So the higher resistance, the better reading we're going to get, the less current we're going to steal from our circuit, we're going to have less loading effects on our circuit. So what we look at with this ohms per volt is how many ohms that I'm going to be adding to the circuit. If I'm looking at a 2 volt range, actually this one's a 3 volt, so let's go with our 20 volt range. If we go back up and look, the 20 volt range had 40 kilo ohms of resistance. That was R2, R1, and the meter all in series. So what happens here is my meter, resistance of the meter is now 40K. And what happens is that 40K is going to affect that 3K. Going through the calculations, what ends up happening is the combined resistance between these two components, with it sitting at 40K and this guy sitting at 3K, R2 essentially becomes 2.79K. So it actually loses us some resistance. So this meter that we just built is not great because it's going to affect the system. If, for example, when we went to measure this and this thing had 400K, the net combined resistance of this guy, 403. So this is going to be at 40K. At 400K, my R3 value, or my R2's value, is 2.978 kilo ohms. So we have a little bit of an effect on it, but not as drastically as that 40K. And so that's the idea behind the selectivities. This gives us an idea that no matter what range we're using, what voltage we're using, doesn't even matter what we're measuring. It gives us an idea of what the circuit is going to do what this meter is going to do to the circuit before we do anything with it. So that selectivity, we want to be as high as we can. Want to be high. Because the higher we are, the more resistance we have, and the more resistance we have, the less we're going to affect anything that it's being used with by putting it in parallel. So when we go to measure things, we have to keep that into account, because there are times where we can load down our circuit and we can actually change the readings of what we're supposed to be getting versus what we are getting when we actually go to measure it. So it's one of the phenomena that we have in electronics that we just have to be aware of and make sure that even if we're doing measurements, that we're using things that have high resistance for voltmeters and we're using them the way that they're supposed to be. And then we shouldn't have any problems with that. And with that, that's a design for a simple four range analog voltmeter. And it's all done, again, just by using the basic meter that we have, the current meter. So now I have that current meter, no matter what its setting is. Now from full voltage, I can have it be any of these ranges. I could go through and pick random values if I wanted to. If I wanted 1 volt, 15 volts, 170 volts, and 6,000 volts, I could design a system for that. And so then when I go in and build it, I can just set it up and go. One of the other cool things about this circuit too is when we have our full and entire circuit, we are not actually building it into a power supply. That current that it's taking, that I meter, is what we are going to siphon out away from our circuit when we go to measure it. So an analog voltage meter is a passive device. We do not have to actively power it to get it to work right, which that in and of itself is pretty cool, that now we have some test equipment that we no longer have to provide power for to make it work. It will just take what it needs from the circuit, and it'll affect the circuit a little bit, but we can mitigate that based on our knowledge and what we have available to work with.